So at this point, we will now discuss one of the applications of the infinite series, which is trying to express a function in terms of an approximating polynomial. So what we will do is we will attempt to we will attempt to write a polynomial that would approximate a given function. Okay. Now this task is customarily done in mathematics um, for the purpose of computations. Okay. The primary purpose of this is is for numerical computations, and later on we will be able to use this technique also to be able to generate uh, polynomials, okay, that would approximate or that would represent a function when we attempt to solve differential equations, okay, having variable coefficients. Okay. So the goal of this lesson is to show how a polynomial function or to show how polynomial functions can be used to um, as approximations for other elementary functions. Okay. So the basic idea there is that if we want to find a polynomial function p that approximates another function f, so this is the approximator. Okay, this is the estimator. We'll call it the estimator or the polynomial approximation. Okay, and this is our given function. Okay, so we would like to write your given function in terms of an approximating polynomial. Okay, so this that would be your p. So this is your approximating. So estimator or approximating polynomial. Okay. So one way to ensure that we will have our approximating polynomial approximate a given function, okay, is that we would like your polynomial and your given polynomial and your approximating polynomial, your FMP, to have the same values at a certain point. Okay. So that is, we would like to have at point C, okay, at point C, at x equals C, okay, we would like both our approximating polynomial and our given function to have the same value. So hence this equation. Okay. So in this case, we said that the approximating polynomial is expanded about C or centered at C. Okay. So geometrically, the requirements that P of C equals F of C means that the graph of P, okay, passes through the point C, F of C. Okay. We can take a look at we can illustrate that using this point. Okay. So since say for example, this is your F, okay, and then this is your P. Okay. This line is your P. Okay. So at this point, okay, at this point where x equals C, okay, and of course, when x equals C, okay, we would like that our f of C has the same value as that of the P of C. Okay, so that's how that is the condition that we would like to impose on our approximating polynomial. That is, it has the same value. Okay, our approximating polynomial has the same value as that of f at point C. Okay, so the thing is that there are many polynomials whose graphs pass through the point C of FC. So aside from this polynomial, there are many other polynomials. Okay, say for example, this one, okay, is another polynomial that passes through that same point. Okay, but is shaped differently from your P. Okay, so there are infinitely many approximating polynomials. If this is the only condition that we would impose. Okay, so our task is to find a polynomial whose graph resembles the graph of f near this point. So we would like our approximating polynomial to be almost of the same shape, okay, as that of your f, okay, as that of your given polynomial, given function, um, at least near that point, at least near C, okay. We would like our approximating polynomial to be of the same shape as that of f, at least near C. Okay. So one way to do that, is to impose additional requirements. Okay. So in this case, you would impose one additional requirement. Okay. That is the slope. Okay. The slope of your approximating polynomial. Okay. At point C is the same as the slope of your given function at point C. So since we're talking about slope, that would be the first derivatives. Okay, that would refer to first derivatives. So aside from having your approximating polynomial uh, assume a certain value, assume the same value as that of your given function, okay, we would also like that at this point, at this very point, okay, the slope of your approximating polynomial, the slope of your approximating polynomial, that is the first derivative of your polynomial at C, okay, equals that of the slope of your given function also at that same point. So that's another condition that we can impose. Okay. So so with these two requirements, then we will be able to have that. So although f and p, okay, you may seem to be baffled that f and p are of different shapes. Okay. Our objective is not for them to have the same shape exactly. We would like them to have the same shape, at least near this point. Okay. If you actually look at that very point, okay, if you look at that point where at C, okay, at C, um, we would see that your approximating polynomial P and your given function F has the same shape, at least at near that point. Okay. It doesn't matter what it looks like outside of it. Okay. It doesn't look like whether they have different shapes here or here. Doesn't matter. What matters is that they have the same shape, at least near this point. Okay. So let's take a look at example 35. For the function f of x equals e raised to x. Okay. Let's find a first degree polynomial p1 of x equals a0 plus a1 x. Okay. Whose value and slope agree with the value and slope of f at x equals 0. So in this case, our c is 0. Okay. The center of our approximation, the center of our approximating polynomial is at 0. Okay. Here we call this first degree. Okay. We have a first degree polynomial here. Okay. We would be at this point, no. When talking about this approximating polynomial, we would be interchanging the term order and degree. Okay, because as you may have as you can recall, degree refers to the power of the polynomial. Okay, but later on, that power is actually related to a certain derivative. Okay, to a certain derivative. So that is why in the case of the approximating polynomial p, okay, degree and order will be interchangeable. Okay, so I may call them first degree, or I may first degree polynomial, approximating polynomial, or I may also call them first order approximating polynomial. Okay, so that would do, because and that only applies to that particular p, which later on will have a particular name. Okay, so what we would the requirements here is that our p1, okay, our p1, which is a linear function, okay, ao plus a1x, okay, will have a value and slope, okay, equal that of the value and the slope of f at x equals 0. Okay, so in that case, we would like to find, so since this is your f, okay, this is your f prime, the first derivative. Okay, now the values of f and f prime at x equals 0 is both 1 and 1. Okay, so we write it here. Okay, so f of 0, okay, remember that f of x is e raised to x, and that our f prime of x, its first derivative, is e raised to x also. So f of 0 is e raised to 0 or 1, and f prime of 0, f prime of 0 is also 1. That's e raised to 0. Okay. Now, what we would like to have is for your p1 of x, okay, to have the same value, okay, and the same slope as that of your function, or as that of your given function. So since our P1, okay, our approximating polynomial is a linear function AO plus A1x, okay, its first derivative, okay, its first derivative is A1, okay, its first derivative is A1. Now what we would like to have is that first we would like to have our P1 at 0 equals f of 0. Okay. So that implies that your A0 plus A1 times 0. Okay, because we have to substitute 0 in x here. Okay. P1 of 0 means you have to substitute 0 onto your x here. So A0 plus A1 of 0 means that we will have this is equal to f of 0. But f of 0 is equal to 1, so we will have this as 1. So therefore, A0 equals 1. Okay, so that's our first condition. Our first conditions imply that A0 must be 1. Okay. Our second condition, which requires that the slope of our approximating polynomial at 0 is equal to the slope of our given function at the same point. Okay. So that means we will have A1, okay, because that's your P1 of x, okay. And we don't have any x to substitute this 0 here. So that remains A1. Okay. Equals f prime of 0 is here equal to 1. So okay, our second condition now implies that our A1 is 1. Okay. So using those facts, okay, or using those values that we have obtained, we will have an approximating polynomial P1 of x as 1 plus x. So 1 plus x approximates, okay, f of x equals e raised to x at x equals 0. Okay, that's the idea. Okay, we would like to find an approximating polynomial for our given function at a certain point. That's the big idea here in this lesson. Okay, so here is the illustration of that. Okay, so this is your P1. Again, we recall that P1 is 1 plus x. So it's a linear function. Okay, it's a linear function. Now, we have here your f of x, the black line. Okay, and as you can see, if you go, or if you actually zoom near here, okay, that line, and that curve of your f of x has actually the same shape. Okay, almost the same shape. Okay, but a better shape, can actually be obtained if we actually increase the degree of your polynomial. Okay, if you actually increase the degree of your polynomial, so instead of having P1 as a linear function 1 plus x, we would actually be obtaining a better approximation, okay, or a better we would have a better approximating polynomial for your f of x if we actually increase its degree or eventually its order. Okay, but how do we do that? Okay, how do we do that? How can we increase that degree of our polynomial, approximating polynomial? To do that, we would like to impose another additional condition into your approximating polynomial. Okay, so the first two conditions is that they should have the same value. Okay, that's the first condition. They should have the same slope. Okay, they should have the same slope. And a third condition might be they should have the same value of the second derivative at that point. Okay, they should have the same value of the second derivative at that point. Okay, so in that case, this is what will happen. Okay, we can have a second degree polynomial. Okay, we can have a second degree polynomial as a0 plus a1 x plus a2 x squared. So now this is a quadratic approximating polynomial. Let me rewrite this instead as p2 of x. Okay, And since we have now three conditions, okay? So the first condition require that P2 of uh, P2 of 0, okay? Since we're creating an approximating polynomial that is centered around 0, okay? So we would like to have our C equal 0. Okay, so we have P2 of 0 should be equal to f of 0. Okay. Second condition is that their slopes P2 prime of 0 equals f prime of 0. Okay, so their slope should be equal at 0. And our third condition is that their second derivatives, okay, P2 double prime of 0 equals f of double prime of 0. They should be equal also. Okay. So we take note that since your f of x equals e raised to x, so f of 0 equals 1, okay? Its first derivative is still e raised to x, so its f prime of 0 is still 1. And we have f double prime of x equals still e raised to x. The derivative of this is still e raised to x, so that f double prime of 0 is still 1. Okay? But in this case, your first derivative, so this is your P2, no? Your P2 prime of x is a1 plus 2a2x. Okay. While your second derivative, okay, your second derivative for P2 is 2a2. Okay. So in this case, let's try to equate. Okay. So for this for this condition, we have um we have to substitute 0 in this case. Okay. So that would imply a0 equals 1. Okay. If we substitute 0 here, this becomes 0, this becomes 0 though. So what is left is a of 0. Okay. And and since f of 0 is 1, so we will have a of 0 equals 1. Next, if we substitute 0 here for your P2 prime, okay, because we want to have P prime of 0, okay, P2 prime of 0, okay, we will have A2, A1, I mean, equals 1, okay, and then here, finally, we will have 2A2, that's your P2 of x, and since we don't have x here, so P2 double prime of 0 is simply A2, okay, equals f double prime of 0, which is 1. So that should imply A2 equals 1 half. Okay. So these are now the coefficients of your approximating polynomial. So our approximating polynomial now, okay, a second degree approximating polynomial for f of x at x equals 0 is 1 plus x plus 1 half x squared. Okay, so look at here. So A0 is 1, A1 is 1, and A2 is 1 half. So you have this as your approximating a second degree or second order approximating polynomial. So at this point, you might have figured out why I can also call this as a second order polynomial. Okay. Mainly because of the second derivative here. Okay, so there. So this second order or second degree approximating polynomial, if you take a look at this one, that would be this curve. Okay. And it would have a better shape than that of P1. Okay. At least near that near x equals 0. Near this point. Okay, at near this point. P2 would have a better shape than would be closely shaped to f of x than P1. Okay, P2 would be closely shaped, okay, than P1 for f of x. Okay, so ayan. Now, so you can see that we can be able to verify later on, okay, by numerical calculations that P2 is a better approximation of f than P1. Okay. Now, if you actually continue this pattern, extending this approximating polynomial, okay, you would be able to get this, this expansion. Okay. So, you're approximating your nth degree or your nth order approximating polynomial for e raised to x would have a form something like this. Okay. So, yun yung this is the idea here. Okay. So, later on, we will be generalizing this for some of your elementary functions. Okay. If you take a look at the values, okay, around your approximating polynomial, okay, and compare them with the original function, okay, considering that we would like to inspect it at x equals 0. This is where we center our approximating polynomial, by the way. So this is the center of P3. Okay, that's the center of your P3. Okay. As you can see that at the center they are equal. Your approximating polynomial and your given function have the same value. But as you can see, as you go farther, either to the left or to the right, okay, the approximations get worse. Okay, it gets the approximations get farther and farther from the given function. Okay, here you would have an error of 0.0004563. Okay, at least that one. Okay, so this is your error for this one. Pero here you would have an error of 0.03. So moving from here to here, your error has increased by how many orders? 1, 2, 3, 4, 5. Okay. So you have already if you increase your distance from 0, okay, or from 0 to 5, you already have increased your order of error by times 10 raised to 5. That's 100,000. Okay. So the idea here, okay, so the idea here is that your approximating polynomial would only work, okay, would only work around a certain value, which is its center. Okay, it would only be, it would only approximate it would best approximate your polynomial near, okay, near its center. Okay, so here, okay, you would be able to see, okay, you would be able to see that if your polynomial is centered here, as you can see here and here, at x equals -1 and at x equals 1, your polynomials, okay, your original, you don't have an original polynomial, but your approximating polynomial actually gets wider variation. Okay. Just here, and then just here. Okay. So they vary widely. Okay. But they actually come close, near the center. So if this is the center of your approximating polynomial, okay, your polynomial would be any degree of your polynomial would be close to the original function around here. Okay, but of course, the higher the degree of the polynomial, the better the approximation. Okay, near here. Okay, it's just that when you go farther, okay, left and right, the approximations made by the approximating polynomial gets worse. Okay, so now we will be able to name that polynomial. Okay, so the polynomial approximation of f of x equals e raised to x, given in example 35, is expanded about c equals 0. Okay. for expansions about an arbitrary value of c, whether so we would like to choose c. Okay, we would like to choose c so that your polynomial is centered around there. Remember that your polynomial, approximating polynomial, would be would be approximated would approximate the given function best at that center. Okay, at that center. Um, so this is our approximating polynomial. Okay. Later on, but at this point, just a little more, we will be able to name that polynomial. Okay. Now, if you actually perform repeated differentiation, okay, because as you can see, our requirements depends on um, the requirements the conditions set for your approximating polynomial depends on the values of the polynomial and its derivatives and the values of the function and its derivatives being equal. Okay, so we would like to get or we would like to perform repeated differentiation for your approximating polynomial. And I hope that even if this is these are a bunch of letters, okay, I hope that you'll be able to get how I hope you'll be able to extract the abstraction of this. Say for example, if you want to take the first derivative, okay, of this one. And this is a skill that you really need to work on because this is something that we will have to do in the next topic. Okay. So we will have so this is 0 because this is a constant. So we will have a1 plus this is a power polynomial. I mean a power term. Okay. So we will have to bring down 2, multiply to a2, and then multiply to x minus c. Okay. So this is you use power formula to get this derivative. Okay. And then the next one to that is 3 times a3 times x minus c square. Okay. And so on. Okay. Which if this one, if you want to get the derivative of this one, okay, that should be bringing down n, okay, multiplied to an, okay, and then you'll have x minus c raised to n minus 1. Okay, that's the first derivative. Okay, its second derivative, okay, double prime. Okay. So this becomes now 0 because this is a constant. The derivative of the constant is 0. Then we will have here 2a, and then the derivative of this is 1. Okay. Plus, this is 3 times 2. Okay. By the way, if you're looking for patterns later on, this is 2 times 1. Okay. This is 2 times 1. Okay. So, that's 2 times 1 multiplied to a2. Okay. Then we have 3 times 2 multiplied to a3 x minus c raised to 1. Okay. And then, as you can see here, the last term here is that we will have it as n multiplied to n minus 1 times a sub n, okay, multiplied to x minus c raised to n minus 2. Okay, so that's the second derivative. So I hope that you will be able to get a grasp of this abstract the abstraction of this differentiation. Okay, and then what we would like to know here. Okay, what we would like to know here is what would be the values. Okay, what would be the values of your polynomials at x equals c. What will be the values of this, including your polynomial? Okay, what will be the values of the polynomial and its derivatives? Okay, at c. So when that if so in that case, if you replace x with c, terms such as this become 0. Okay, so that is why at c, okay, at c, this becomes a0. Okay, this one, everything here becomes 0. So what is left is a1. Okay. For the second derivative, everything with x minus c becomes 0. Okay. So what is left is a2. Okay. And then in general, okay, The last derivative kasi is merely a constant. Okay? If you take the nth derivative of this, this thing, okay, if you take the nth derivative of this thing, the last of that would be a constant. Okay? Say for example, you have something like a polynomial of the fourth degree, x to the fourth plus 3x cubed plus 2x squared plus x minus 3. Okay. If you take a good look at this one, if you take the fourth derivative of this, okay, if you take, we'll write fourth derivative this way, okay. If you get the fourth derivative of this, that simply is a constant already, okay. It's more of like 4 times 3 times 2 times 1. So that's 24. Okay. We'll be getting it from here. Because in the first derivative, that becomes 4x cubed. In the second derivative, that becomes 4 times 3 times x squared. In the third derivative, that becomes 4 times 3 times 2 multiplied to x. So therefore, for its fourth derivative, it would become 4 times 3 times 2 times 1. So 24. And it's a constant. That's the nth derivative of a fourth degree polynomial. So the nth degree or the nth derivative of an nth degree polynomial is a constant. And that constant is this one. Okay, that's n factorial multiplied to af. Okay. So now, because we would like to agree, we would like to have we would like our function values and their derivatives agree with the values of the polynomial and their derivatives. Okay, agree at a given point C. Okay, we would be able to equate them. Okay, as this one. Okay, so as what we did here. Okay, so as what we were able to do here. Okay, so we have their function values equal at x equals 0. Okay, we have their first derivatives equal at x equals 0. We have their second derivatives, okay, to be equal at x equals 0, and so on. If you do that, you'd be able to solve a0, a1, the coefficients of the polynomial. Okay, and those coefficients would turn out to be this. Okay, would turn out to be this numbers. Okay, so with these coefficients, these are not the coefficients of your approximating polynomial. These are the coefficients of approximating polynomial Pn of x. Okay. Now, with these coefficients, we can obtain the following definition of Taylor polynomials. We actually call this approximating polynomial as Taylor polynomials. By the way, if you're wondering, the theory behind the Taylor polynomials and Taylor series that was presented in your activity 4 in the laboratory is this. Okay. So we call them Taylor polynomials, named Taylor polynomials and Maclaurin polynomials. Okay, so we'll settle the difference between the Taylor polynomial versus Maclaurin polynomials in this definition. Okay. So at least now, if you hear the name Taylor, it's not only the singer that would just pop up into your mouth. You now have a mathematical idea, okay, that would counter that notion that Taylor is just a singer. Okay. So definition of Taylor polynomial and nth Maclaurin polynomial. Okay. So if f has n derivatives at c, okay, then the polynomial, okay, As you can notice, replaced, we now have replaced your your Taylor polynomials, I mean your coefficients with your AO, A1, A2, and AN up to AN with this values based on your function values, okay, and their derivatives. Okay, we have already replaced them. Okay, so this is now called the Taylor polynomial. Okay, the Taylor polynomial is is an approximating polynomial centered, okay, at x equals c. Okay, so it's called the nth Taylor polynomial for f at c. The center is at c. Now, a special condition or a special case for Taylor polynomial is when c is equal to 0. Okay, so when c is equal to 0, then what will happen to your Taylor polynomial is this. Okay, and this is called now your Maclaurin polynomial. Okay, this is called the Maclaurin polynomial. So here's the difference between a Taylor polynomial and a Maclaurin polynomial. The center of the Maclaurin polynomial is 0, while the center of the Taylor polynomial is any arbitrary number. Okay, that's their difference, and that's their only difference. Okay, as per definition, pero they would differ greatly depending on the function that we consider. Okay, so but when you are asked what is the difference between a Maclaurin polynomial and a Taylor polynomial is its center. Okay. The center of the Maclaurin polynomial is 0. Okay. While Taylor polynomial can be centered anywhere. Okay. So the n here, okay, the n here is the order or the degree. As I stated, I will be interchangeably be referring to this n as either the order or the degree. Okay. Degree because it refers to a polynomial. Order because there are derivatives involved. That is why I would be interchangeably using them. Okay. Okay. Let us find the nth Maclaurin polynomial for f of x equals 0. Okay. So as we will be again, the general formula for the nth order coefficient is um, f nth derivative of f at c over n factorial. Okay? So that's the ito yun ayan. So that's the nth order coefficient for your Taylor polynomial. This becomes the nth derivative of f at 0 over n factorial for a Maclaurin polynomial. Okay? So in this case, if we would like to if we would like to find the Maclaurin polynomial for e raised to x. Okay, we would like to find um the Maclaurin coefficients. Okay. So A1, okay, or A0 is simply the zero order derivative. So that's basically your function. So f of 0 over 0 factorial. Okay. And we would have here, take note that f of x is e raised to x. And luckily for us, the derivative of this is the same as the function itself. So f of x equals e raised to x, f prime of x is e raised to x, f double prime of x is e raised to x, and so on. Okay. So from here, a of 0 is f of 0 over 0 factorial. So f of 0 is e raised to 0. Okay. So that is 1 over 0 factorial is 1. So a of 0 is 1. Okay. As what we have been, as what we were able to determine earlier in an earlier example. So a1 is the first derivative of f of 0 over 1 factorial. Okay, so again, f prime of 0 is is e raised to 0, so that's 1. 1 factorial is 1, so this is still 1. Okay, so a2 equals f double prime of 0 over 2 factorial. Okay, so f double prime of 0 is e raised to 0. Okay, it's still e raised to 0. So this is 1 over 2 factorial is 2. So this is 1 half. Okay. A3 is a triple prime of 0 over 3 factorial. Okay. So the third derivative of your e raised to x, okay, is still e raised to x. So therefore, the third derivative of f at 0 is e raised to 0. So that's still 1. So 3 factorial is 6. 3 times 2 times 1. Okay. So a4 is, excuse me, fourth derivative of f at 0 over 4 factorial. Okay. Which is, yeah, the fourth derivative of f at 0 is still e raised to 0. So that is still 1. 4 factorial is 24. Okay. And later on, if your factorials gets cumbersome to write because it gets too large, you can actually just retain to write it as a factorial. So instead of actually writing it as 6 or 24, you might prefer it to write still it as 3 factorial or as 4 factorial, because later on that would get really cumbersome to write. Okay. So given this the nth Maclaurin coefficient, okay, the nth Maclaurin coefficient now is the nth derivative of of f at 0 over n factorial. And still, since the nth derivative of e raised to x, okay, the nth derivative of e raised to x is still e raised to x. Okay, how many times you get the derivative of this is still it's e raised to x. Okay, so that the nth derivative of f at 0 is still e raised to 0, so that's 1 divided by n factorial. So these are your Maclaurin coefficients. So this is now your Maclaurin polynomial. So Pn of x, okay, the nth order Maclaurin polynomial is a0x plus a1x, sorry, wala pa lang x to. Okay, so ulit. This is a0 plus a1x plus a2x squared plus a3 x cubed plus a4 x to the fifth and so on. Sorry, x to the fourth. And until a sub n, x raised to n. Okay, and so on. Okay, so therefore, we substitute this Taylor this Maclaurin polynomials, okay, I mean coefficients, okay, into this. So we will be able to write the Maclaurin polynomial, okay, as a0 is 1, a1 is 1 times x, so that's x. a2 is 1 over or 1 half or 1 over 2 factorial na lang, no? Let's write this instead as 1 over 2 factorial. Okay, so 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x raised to 4. And the nth, okay, the nth order coefficient for your Maclaurin polynomial is 1 over n factorial x raised to n. Okay, so this is now your n order approximating polynomial for your e raised to x, centered at c equals 0. Okay, so that's centered at 0. Okay. So let's try to find the Taylor polynomials P0, P1, P2, P3, and P4. Okay. For f of x equals ln x centered at c equals 1. Okay. So that means our x our Yeah, our center is at 1. Okay, so we're looking for Taylor polynomials because the center is non-zero. Okay, so we start off with this one. Let's try to again, this will be your general formula for your nth order Taylor polynomial. Okay, so it requires us to evaluate your nth order derivative. Okay, so since we look for uh, this is your original function, this is a first, second, third, fourth derivative. We need to find the fourth derivative of we need to find up to four derivatives of um up to the fourth derivative of ln of x. Okay, so we will have f of x equals ln of x. Okay, our first derivative, f prime of x is 1 over x. Okay, our second derivative is negative 1 over x squared. Okay, our third derivative, okay, is that's 2, positive 2 over x cubed. And our fourth derivative should be written this way. Okay, should be negative I think 6. That's 2 times 3. Okay, so that's yeah, let's write the 6 over x raised to 4. Okay, so those are our derivatives. Okay, so let's evaluate those. Okay, at 1. Okay, we'll evaluate those at 1. So therefore, f of 1 is ln of 1. So that's 0. F prime of 1. Okay, remember we have to evaluate this at c. Okay, so that's why I have to substitute 1 here. Okay, so f prime of 1 is 1 here. Okay, f double prime is negative 1. Okay, f triple prime is 2, and f to the fourth derivative of f is negative yeah, nakalimutan ko nga. I forgot to write it as f double prime of 1. So that is negative 1. F triple prime of 1. Okay, it's f triple prime of 1 is 2. And f or fourth derivative of f at 1 is negative 6. Okay, so our Taylor coefficients, okay, our Taylor coefficients are them, okay, are them. For a0, that's 0 over 1. Okay. Actually, this is 0 over 0 factorial. If you would like to generalize it, this is 0 over 0 factorial. So 0 over 1. Okay. Oh, that's in the 0. Let's write it as 0 na lang. Okay. Then a1 is 1, okay, over 1 factorial, or 1. Okay. A2 is negative 1 over 2 factorial, okay, or 2. Okay, yeah, 2 factorial. Okay. A3 is 2 over 3 factorial, okay, and A4 is negative 6 over um, negative 6 over 4 factorial. Okay. Now, our Taylor polynomial then, okay, our Taylor polynomial then becomes, okay, this is how we write it now. P4 of x is A0 plus A1 multiplied to x minus 1. This is 1 because that's our center. That's x minus c. Okay. Recall it from the definition of the Taylor polynomial. So, x minus 1, okay, raised to 1, okay, plus a2, x minus 2, x minus 1, square, plus a3, x minus 1, cube, plus a4 times x minus 1 raised to 4. Then we substitute the Taylor polynomial. So we will have here A1 is 1, so this is x minus 1 plus A2, A2 is negative, so that's minus 1 over 2 factorial times x minus 1 squared. This is positive, so plus 2 over 3 factorial, okay, times x minus 1 cube, okay, minus 6 over 4 factorial multiplied to x minus 1 raised to 4. That's your P4. And then, you can simplify this, okay, as this is x1, okay, 1 over 2 is 1 half x minus 1 squared. 2 over 3 factorial is 2 over 6. So that's 1/3. Okay. So that's 1/3 times x minus 1 cube. Okay. Then minus 6 over 4 factorial is 6 over 24. So that's 1/4 x raised to x minus 1 raised to 4. So this is our fourth order Taylor polynomial for ln of x. Okay. So you can actually compare the graph of just P1, P2, P3, P4. Take note, this is how it evolves. Okay. You don't have P0 because P0 turns out to be 0. Okay. But this is your P1. Okay. That is your P1. Ito lang. X minus 1 lang. Your P2 is this. Okay. That is your P2. Wait. So this is your P1. Okay. Your P2 is this. Okay. That's your P2. Okay. Your P3 is this. Okay, that's your P3. And then your P4 is the entire thing. That's your P4. So, as you can see, your P1 is simply a line. Okay? But your P2 is now a quadratic, a parabola. Okay? Your P3 is this. Okay? And your P4 is this. So, as you can see, the shape of your polynomial, okay, the shape of your polynomial gets to be closer and closer, okay, to the function. Okay, as you increase the order or the degree of your approximating polynomial. So as n increases, n here means the order of the approximating polynomial. So as your n increases, the graph of Pn, okay, the approximating polynomial becomes a better and better approximation of the graph of f of x equals ln of x near x equals 1. At least near x equals 1. Okay. So that's the purpose of what we are doing so far. What we would like to know, or what we would like to do here, is that we would like to come up with a polynomial that would approximate our function. Okay. So and that is what the Taylor polynomial and the Maclaurin polynomials are for. Okay. So I think I can leave you to work on example 39. Okay. Just remember that when you work on this, the n order coefficient is f, the derivative of f, the nth derivative of f at c, okay, and divided by n factorial. Okay. So here, since you're looking for P0, P2, P4, and P6, that requires the function, okay, f of x equals cosine of x. Okay. The second derivative, it requires the second derivative. It requires the fourth derivative. Okay. And it requires the sixth derivative. Okay. And then you have, since this is a Maclaurin polynomial, the center is at 0. Okay. The center is at 0. Okay. So that's what you need to remember in working on this example 39. And the results would be this one. Okay. And if you actually graph P6 and compare it to cosine of x, you would see that at x equals 0, okay, or at the center, okay, your P6 is very, very close in shape as that of your original function. Okay. Now, let us note in example 39 that the Maclaurin polynomials for cosine x have only even powers of x. You can actually verify that by computing, okay, by computing what are the Taylor coefficients, or what are the Maclaurin coefficients for P3, okay, for P1, P3, and P5. Okay. Because the Maclaurin coefficients for this I mean, hindi pa yan. If you actually compute the Maclaurin coefficients A1, A3, and A5, this would all turn out to be 0 for cosine. Okay, so that is why your cosine function can be approximated by the even coefficients of your Maclaurin expansion, or Maclaurin polynomial. Okay. In the same manner, that also goes through with sine, but in this case, your even coefficients are now 0 instead of the odd coefficients. So for sine, you would be able to get something from A1, on A1, A3, A5, and so on. But A2, even A0, okay, A4, and A6, all of this would be equal to 0. So here's the thing about the cosine and the sine function. Okay. The Taylor polynomial for sine function are composed of odd powers of x. Okay, while the Taylor polynomials for the cosine are composed of even powers of x. So you'd be able to figure that out kapag if you're able to work on example 39 and example 40. Okay. So I would like you to verify those observations for cosine and sine. Okay. From example 39 and example 40. Okay. So now let's have a let's approximate the value of ln 1.1 for using a Maclaurin polynomial. Okay. And although you were able to obtain, okay, a fourth order Maclaurin polynomial from example 38, okay, which is I hope you can remember this, x minus 1. There, I hope I was able to remember. X minus 1 minus x minus 1 minus 1 half plus 1 third minus 1 fourth. Sige. Maalala ba? X minus 1 minus 1 half x minus 1 square, okay, plus 1 third x minus 1 cube minus 1 fourth x minus 1 raised to 4. Okay. So that's a Taylor Taylor polynomial. Actually, Taylor polynomial pala to. Ito nakuha natin sa kasi may center siya at 1. Okay. So since we are asked to find a Maclaurin polynomial, okay, so Maclaurin polynomial pala yung pinapahanap sa atin. Okay. So we'll just simply set this center here to be 0. Okay. We'll obtain the same coefficients. Will contain the same set of coefficients here. Although ang ginawa pala niya dito, I'll solve it na lang. I would like to solve it kasi on the basis of what we were able to obtain previously, but apparently iba pala yung technique na ginawa niya. So anyway, the technique that I am proposing would still work. Okay, later on pakita natin. But here, since Maclaurin polynomial, okay, Maclaurin polynomial, yung ating what is being asked is to use a fourth Maclaurin polynomial to approximate the value of 1.1. Number one, the center of that should be at 0. Okay. But the thing is that if we use ln of x, okay, as our f of x here, Okay. And what is being approximated is that x should be equal to 1.1. Ang layo ng 0 sa 1.1. So, in this case, the Maclaurin polynomial for f of x would actually give us a very erroneous, a very grossly approximated value because napakalayo ng c, okay, with that of what is being asked for us to evaluate, which is ln of 1.1. So instead of using that, let's use f of x equals ln of 1 plus x. Okay, we'll use ln of the natural logarithm of 1 plus x. Okay, so that although the center is still here is 0. Okay, the center is still here is 0. At least we would be working around. Okay, we would be working around ln of 1 plus 0 or ln of 1. Okay, which is very close to ln of 1.1. Okay. So, yung natin, yung Maclaurin polynomial natin is approximates actually ln of 1. Okay. But using this to approximate ln of 1.1 would not be that would not be that bad. Kasi hindi naman masyadong malayo yung 1 sa 1.1. Okay. Again, if the center is at 0 and if this is the center, okay. Okay, and you try to approximate something at 1.1, that's very far. Okay. So, your Maclaurin polynomial, again, poorly performs when you are too far from the center. So, what we will do is instead of using ln of x, because if you center that at 0, okay, the center of your your function value would be ln of 0. Okay. So, that would have a very our approximation would be egregiously far from what we would like it to be. Okay. So what we would like to do is instead of approximating the polynomial for f of x equals ln of x, we'd like to approximate or we would like to create an approximating polynomial for ln of x plus 1. Okay, so that kung nasa 1 yung i-approximate natin, okay, your function value is at ln of even if the center is at 0, okay, what it would evaluate is ln of 1. Okay. So therefore, yung approximation nyo would not be that too far. Okay. The shape of the shape of your polynomial would be very close to ln of x plus 1 at 1.1. Okay. At 1 and at 1.1. Okay. So again, habang lumalayo tayo doon sa center ng ating approximation, okay, we would have a very egregious approximation. The approximation becomes very poor. Okay. So here we would like it since we're looking for coefficients, since we have to use fourth order Maclaurin polynomial. We would like to have f of x equals ln of 1 plus x. Okay. Its first derivative is it's 1 over 1 plus x. Okay. Its second derivative, okay, is negative 1 over 1 plus x squared. Its third derivative is 2 over 1 plus x cubed. Okay. And its fourth derivative, okay, is at negative 3 over 1 plus x raised to 4. Okay. Now, the center of our, since this is a Maclaurin polynomial, the center of our approximation is at 0. Okay. So, we evaluate now f of 0 here. So, f of 0 here is ln of 1, which is equal to 0. I'm not sure. Bigla ako naging sigurado. So, ln of 0 is 1. ln of 1 is 0. Okay. Then next, we have f prime of 0 is 1 over 1 plus 0. So, that's 1. Okay. f double prime of 0 is negative 1 over 2 square. Okay. Yeah, negative 1 over 2 square. So that's 4. 1 over 2 square. Yeah. Ay, 0 pala to. So 1 over 1 square lang pala. Okay, so that's negative 1. F triple prime of 0, the third derivative of f is 2 over 1 cube. So that's 2. Okay. And the fourth derivative of f at 0 is negative 3 over 1. So that's negative 3. Okay. So these are your function values and their derivatives at c equals 0. So the coefficients now, okay, a0 is simply 0. Okay. a1, okay, is f prime of 0 over 1 factorial. So that's 1 over 1 or 1. a2 is f double prime of 0, okay, over 2 factorial. So that's negative 1 over 2 factorial, or basically that's negative 1 half. a3 is f triple prime of 0 over 3 factorial. So that's 2 over 6 or 1/3. Okay. And a4 is fourth derivative of f at 0 over 4 factorial. So this is negative 3. Sorry, hindi pa to negative 3, no? This should have been 6. Kasi 2 times negative, that's 2 times negative 3. Kaya negative 6 to. So this is negative 6, sorry. So this is 6 over 1. So that's negative 6. So this is negative 6 over 24 or negative 1/4. Okay. So those are your Taylor or Maclaurin coefficients. Okay. So we write now the fourth order Maclaurin polynomial for ln of x plus 1 as the 0. Then we start with 1 times x, okay, minus 1 half times x square, okay, plus 1/3 times x cube, okay, minus 1/4 times x raised to 4. Okay. Now, if we want to evaluate the logarithm of 1.1, okay, and use our function here, okay, it should mean that ln of 1.1 is f of 0.1. Okay? Kasi may 1 na yung function natin. So x here becomes simply 0.1. Okay? So that means you would have ln of 1 plus 0.1 there. Okay? So therefore, ang x natin, this is our x now. X is our 0.1. So that if we want to approximate that, okay, using our polynomial, our Taylor Maclaurin polynomial, so you would have 0.1 here. So this is x, or this is 0.1 minus 1 half times 0.1 square plus 1/3, okay, times 0.1 cube minus 1/4 times 0.1 raised to 4. Okay, we'll be able to compute that, okay, as 0.1 minus 1 half times 0.1 squared, okay, plus 1/3 times 0.1 cube minus 1/4 times 0.1 raised to 4. So our approximate value is 0.953. Okay, so let's have it as 0.09538. 0.09538 0.08333. Okay, let's use that value. But we take note that the natural logarithm of 1.1 is around 0.0953 10178. So at least we were able to get 1, 2, 3, 4 decimal places. Okay. The natural logarithm of 1.1 equals 0.0953 101,798. Okay. We were able to get 4 decimal places. 1, 2, 3, 4. 1, 2, 3, 4. We were able to get 4 decimal places. Correct. Okay. So, for our approximating polynomial. Okay. And for you to be able to come up with an exact value for this one, you need to use a large number of terms for your approximating polynomial. Okay? So that's how your Maclaurin polynomial works. Okay? And I think there are analysis tables here. Okay, so yun na nga, now, if you actually take a good look, okay, if you actually take a good look at the effect of the terms used in the approximation polynomial is, as you actually increase the term, you actually get closer and closer. You actually get closer and closer to the value. Okay. So increasing the number of terms. Okay. Increasing the number of terms. The number of terms of the approximating polynomial increases the accuracy. Okay. So that's one. Okay. On the other hand, we can also take a look at how the fourth order polynomial changes as x is increased. Okay. If we actually remember that the center of our approximation is at 0. Okay. The center of our approximation is at 0. Okay. As you actually go further from 0, okay. As you actually go further from 0, your approximation becomes worse and worse. Okay. So this is the value of your ln of x. Okay, ln of 1 plus x, I mean. Okay, and as you increase your x from 0 to 0.1 to 1.5, okay, and so on. Okay, and compare it with how your approximating polynomial performs. As you get further and further from this, okay, your approximation gets worse. Okay. This is what I have been pointing out in your activity. Okay. This actually pertains, this one, the space between this, okay, is what I have been referring to as the step size. Okay. In numerical calculations, this difference is what we call the step size. So, the error between the actual or the exact polynomial, the exact function and the approximating polynomial becomes smaller and smaller if the step size is made being small. Okay, if you make your step size smaller and smaller, your error becomes smaller and smaller also. And here, okay, in here, as you actually increase your order, as you increase your number of terms, your approximation gets better and better. Okay, so example 41 illustrates two very important points about the accuracy of Taylor or Maclaurin polynomials for use in approximations. Number one, the approximation is usually better for higher ordered Taylor or Maclaurin polynomials than those for the lower order. Okay, so the higher the order you use for your approximating polynomial, the better for the approximations. Okay, and the approximation is usually better at x values close to c than at x values far from c. Okay, so if you actually get farther and farther from the center of the Taylor or the Maclaurin polynomial, you actually are committing more and more errors for your approximation. So you have to remember these 2 points. Okay. Now, we proceed with in the discussion of how accurate, okay, how accurate your approximation was. Okay. Um, Remember that that the basis of our accuracy up to this point is hinged on the fact that you know what would be the true value, okay, of your function. But that's not the but that's not the case uh at all times. Okay. There are cases in which we will use the Taylor polynomial to approximate a certain function value. Okay. But we really don't know what the actual or what the true value of the function value is at that point. Okay. And that happens that that doesn't that those situations are not really that uncommon in engineering. Okay. So we discuss here the remainder of the Taylor polynomial, in particular the Taylor's theorem. Okay. So to measure the accuracy of approximating function value of f of x by the Taylor polynomial p, okay, we can use the concept of the remainder defined as follows. Okay, so we remember if we are making an approximation to a known function, okay, then the difference between them, okay, the difference between the value of the function and the value of the approximating polynomial is its error. Okay, this is error. So therefore, the remainder, we call this the remainder. Okay, we call this the remainder, and basically that's also also the error. Okay, error of your approximation. Okay, so since from here we will be able to have your remainder as the difference between, okay, the difference between the function value and the approximating polynomial. Okay, so the absolute value of the remainder is called the error. Okay, or basically the truncation error, as discussed in your activity 4. Okay, so that is the error, is the absolute value of the difference between f and p. Okay. So Taylor's theorem, also the next theorem, gives a general procedure for estimating the remainder associated with a Taylor polynomial. So we call this theorem the Taylor's theorem. Okay. And the remainder given in the theorem is called the Lagrange form of the remainder. Okay. So, ang sabi ng what theorem 19 or the Taylor's theorem states is that if a function f is differentiable through order n plus 1 in an interval I containing C. Okay. You have an interval I. Within that interval is the number C. Okay. So you have a low x and a high x. Okay. And within it, so this is your interval. Okay. And within that interval is a number C. Okay. Is the center of your is the center of your approximation. Okay. Then for each x in this interval, there exists a number z. Okay, there exists a number z between x and c. Okay, so if say for example, that this is the center, this is where your center of your approximation. Okay, so that's x equals c. Okay, there's a number between say for example, this is your x. Okay, tapos ito yung c niyo. Okay. Okay, ganito. Instead of actually saying that there are two numbers involved, let's just involve x and c. So let's just involve them. Okay. Since both of them would be in the same interval naman. Okay. There exists a number So the endpoint of your is x and the other endpoint is c. And this is where the center of your polynomial is. Okay. Now there exists there exists z between x and c such that the remainder, okay, the remainder is evaluated as this one. This is called the Lagrange form, okay, of the remainder. Okay, so we will be able to evaluate that error if you know this number c. Okay, if you know that number c. uh, in which in most cases we don't know that number C. Okay. We really don't know that number C. What we know of is that that number C is within this interval between X and C. Okay, it's within X and C. So that what we can only have is a maximum, or is a parang um an upper bound for your error. Okay. And that upper bound for your error is actually is given as this factor. Okay. So that's the upper bound of the error that that your approximation can commit. Okay. So for n equals 0, the Taylor's theorem states that if f is differentiable in an interval I containing C, then for each x in I, in there exists between and such that um, f of x equals f of c plus fz of fz times x of c. Okay. So if we actually try to compute for, or try to find an expression for this from from zero order. This is a zero order polynomial. Zero order P0. Zero order Taylor polynomial. Okay. We can be able to find an expression for your f prime of z, which is this one. Okay. Which is an expression for the mean value theorem. Okay. The mean value theorem, if you can remember, states that the mean difference between 2 points in your in your in your interval, okay, is equal to the slope. Okay, so parang you have a curve, you have a curve something like this. This is f of x, okay, and then this is f of c. Sorry, say this is x, so this is f of x, and then say for example this is c, so therefore this is f of c. Okay. The slope here, okay, the slope here is actually equal to one of the slopes here. Okay, parang the geometric interpretation of the mean value theorem is that within this interval x c, between x and c, okay, there is a slope, there's a slope line that is parallel to this. Okay, this is your slope. This is your slope here. Okay, this slope is this one. Okay, now the mean value theorem states that in between x and c there is a slope here. Okay, that is parallel to this slope line. Okay, so that's the mean value theorem. When applying Taylor's theorem, you should not expect to be able to find the exact value of z. That's what we were pointing out. We don't know that value of z. If you could do this, okay, because if you can do that, then an approximation is not needed. Okay, what we would like to find is bounds. Okay, especially an upper bound. Okay, if we are able to find an upper bound for z, okay, then if actually z is smaller than that, which is usually the case, then we can confidently say that our polynomial is sufficiently approximated. Okay, because if the error is this, if your approximate error is this, okay, that's the upper bound for your remainder, for example. Okay, that's the upper bound for your remainder, and the actual error is this. Okay, so um that's a good sign that we were able to sufficiently approximate your ano. Okay, so yeah, um let's try to test that idea in example 42. Okay, so the third Maclaurin polynomial for sine x is given by this one. Okay, actually if you work on example that involves sine above, okay, which involves approximating sine of pi over 6 yata yun. Okay, you'll be able to get this one. Okay, now use Taylor theorem to approximate sine point 1 by the third order polynomial and determine the accuracy of the approximation. Okay, so um if you use Taylor's theorem, we would be able to specify that your sin x is the Taylor polynomial plus the remainder. Okay, that's what the Taylor polynomial, Taylor theorem states. Okay, so your function value is the polynomial. Okay, it's the polynomial plus the remainder. Okay, so here we would have x minus x cubed over 6 plus the error or the remainder. Okay. Now, since our center, okay, the center here is 0, since this is a Maclaurin polynomial, and that we would attempt to evaluate it at x equals 0.1. Okay. Then our z is between 0 and 1, and 0.1, as stated in Taylor polynomial. Okay. So our z would be between 0 and 0.1. Okay, and we don't know the exact value of z there. Okay, because we are just trying to approximate now your sine of sine of 0.1. Okay. So the approximate value then of sine 0.1 as given by the Taylor polynomial is what? 0.09833. Okay. Now, let's look at the error now. Okay. The error now involves the fourth derivative of your function. It involves the fourth derivative of your function. Remember that your original function, okay, our original function is sine. Okay. So its first derivative is cosine. Okay. Its second derivative is negative sine. Okay. Its third derivative is negative cosine. Okay. And the fourth derivative of sine x, okay, is still sine x. Okay. So it means that so we will have here sine x now. Okay. So it means that we can actually evaluate the error, okay, on the basis of f to the fourth z over the Lagrange form, fourth factorial, which is sine x, sine z, okay, over 24, okay, times times x to the fourth. Kalimutan ko lang x to the fourth. Times x to the fourth, which is equal to sine of z. Okay. Times 4 factorial over x raised to 4. Okay, or 0.1 raised to 4. We know x is 0.1. Okay, but we don't know what sine is. What z is. So therefore, it would be virtually impossible for us to compute for sine of z. Okay. But if you would be thinking about this now, since your say ranges from 0 to 0.1, okay, the maximum value, okay, or the maximum, and since we don't know what z is, okay, the upper bound, okay, the maximum error that you can actually have, since sine of 0.1 worst case, okay, is just a decimal. So then the maximum error that you would be able to incur, okay, would be x raised to 4 over 4 factorial. Okay, that's the maximum error that you can incur. So therefore, this error would be between 0 and x raised to 4 over 24. Okay, remember that this is the exact value of the error. But since the knowledge, or the fact that we don't know what z is, okay, we would like to know, or we would like to have an upper estimate, okay, of an upper bound for that error, okay. And that maximum error would be dependent more on the x raised to 4 over 4, since sine of z, which is between these values, is negligible compared to x raised to 4 over 4 factorial. Okay, so that we will put it as the upper bound of your error. So your error is between this. Okay, in between 0 and by the way, this 0 is because the lower bound of your z is 0 and sine of 0 is 0. So that's the lower bound for your error. But the upper bound, we're concerned more of the upper bound. Okay, the upper bound would be that your error would be x raised to 24, x raised to 4 over 24. So think of it this way. For us to be able to determine the upper bound, no? Your error, okay, the exact value of error is given as sine of z over 4 factorial times x raised to 4. Okay. Now, since your say would be between 0 and zero point 0.1, and we're not really sure how your say would behave here, and the exact value of z here. And given that this is a sine function, we really don't know um, the behavior of sine say inside this interval. Okay, there is a certain value of sine z that would be maximum here. Okay, but um what we're sure of is that if we actually, since the value, since your sine say, okay, if you actually choose a value between 0 and zero point 0.1, we would know that your sine say, okay, your sine say would actually be less than 1 and greater than 0 in this case. Okay, and in that case, if you actually, whatever the value of sine say here is, um since your error is given in this manner, we would just use the maximum value x raised to 4 over 4 factorial, because any whatever value that you multiply it with the sine say, whatever value of sine say you multiply it to this that will just be less than, okay, that will just be less than the value for x raised to 4 over 4 factorial. So we will set this to be the maximum error. It's the upper bound of your error. Okay, so that is why we will use that. Okay. We are choosing this basically because we are thinking that this is a value that is less than 1, and if we multiply it here, it will just lessen the value of your r. Okay, and the thing is that we don't really know what z is. Okay, but what we're really sure of is that if we multiply this to this, it would just lessen the value. So that we will be able to get a maximum. Okay, get a maximum value. We'll just use this as the upper bound. Okay, we'll just use this as the upper bound of your error. So that is why our error is, the upper bound of your error is this, 0.1 raised to 4 over 24, which would be 0.000004. Okay. So that's the upper bound of your error. Okay. Now, the actual value of your sine point 1, okay, would now lie between the approximate value, which is 0.09833, plus the lower bound for your error, which is 0. Okay. And 0.099833 plus the upper bound of your error, which is 0.000004. That is where your actual value of sine point 1 would lie. Okay, so that is this interval. This is that is this interval. Okay. Okay. By the way, one thing that we would also like to not do is to actually evaluate sine of point 1 from the error, because yun nga yung in-estimate natin. We are trying to estimate sine of point 1. And it would be really absurd for us to compute for sine of 1 as part of the error analysis, whereas we really don't know how to compute sine of 0.1. Okay, I hope you get that idea. Okay, so the actual value, a calculator value for your sine of 0.1, okay, is 0.09983341665. So that are we within that interval? 833. So here is the ito yung lower bound. Okay. So since the upper bound is 834 na. Okay. So yeah, this is within sine point 1 is actually within this bound. So our estimate is actually correct. Okay. So ito yung pinapoint out ko kanina. It would be really absurd for us to compute for sine of z here. Okay, because that's the one thing that we were trying to estimate. Okay. So that is why it is really practical for us to use just this as the the upper bound for your error. Okay. Now let's do that again. Or let's try to understand it further by examining example 43. So let's determine the degree of the Taylor polynomial expanded about C1 that should be used to approximate ln of 1.2 so that the error is less than 0.1. Okay, here the thing is that baliktad naman yung gagawin natin. We are given the error. The question is how much of the Taylor polynomial, how much condition do we have to pose on our Taylor polynomial to be able to approximate it with that specified error. Okay. So the Lagrange error for your Taylor polynomial for this is Taylor polynomial at C1 at C equals 1, so 1.2. So therefore we can use ln of x here. Okay, so your f of x here is ln of x. Okay. Or basically that's ln of x minus yeah, so it's ln of x nga, tama. Okay. So its nth derivative, okay, we can find its nth derivative by what you need to do here is to find a pattern for the nth derivative. Okay, so let's look for some pattern. So the first derivative is 1 over x. The second derivative is negative 1 over x squared. Okay. The third derivative is 2 over x cubed. The fourth derivative is negative 2 times 3 over x raised to 4. Kaya naman natin humanap ng pattern dyan. Number 1, we have an alternating pattern. So negative 1 raised to n might be a useful factor. Okay, so we have here, since the odd terms are positive, so we have this as the okay, we have this as one of the factors. Okay, next is that we start with the numbers. There's no question about the denominator. That's simply x raised to n. N actually pertains to the derivative. Okay, to the order of the derivative. Okay, so yung first order derivative ninyo is 1. Okay, so that's x raised to 1. Yung second order derivative nyo is 2. So this is 2. Okay, so yung problema na natin is yung number. Okay, so it seems that it would be something like if this is 4, this is 2, 3. If this is 3, this is 2, 1. If this is 2, this is simply 1. Okay. And if this is 1, this is just 1. Actually, we're okay. Madali yung pattern dito, tsaka dito. But it would come under question here and here. Okay, so here are the patterns. When n equals 1, you have 1. When n equals 2, okay, you have 1. Okay, when n equals 3, you have 2, which would have came from 2 times 1. Okay, it would have came from 2 times 1. Okay, so when n equals 3, okay, when n equals 4, this would have been 6. Okay. But this pattern is actually a pattern for the factorial. Yun yung wala naisip. Okay. So this is 1, 1. 1 is 0 factorial. This 1 is 1 factorial. 2 is 2 factorial. 3 is ano? I mean 6 is ano? 3 factorial. Okay. Ang susunod kasi dyan is what's next after that is a positive number. So this is 2 times 3 times 4 x raised to 5. Okay. So that's 2 times 3 times 4 is 24. Eh. So this is 24. Okay. That's for n equals 5. So that's 4 factorial. So as we can see, that's n minus 1 factorial. Do we, ano? Ayan. So, ayan. Nakuha natin siya dito. Okay. So that's the nth derivative now. The nth derivative of your polynomial. That's negative 1 raised to n. That's n minus 1 factorial over x raised to n. And again, this is something that I would like you to, I would have your, I would have your your skills for inductive reasoning would be very, very useful. Okay. We will do this more often. That is to discern patterns out of a certain set of a certain set of derivatives, for example, or numbers or whatnot. You'd be able to you need to get a pattern or a general term out of that. Okay, so we have this as your end term, no? Okay. And remember, just remember that our error, okay, the Lagrange form of the error is the nth derivative of f at z over n factorial, okay, multiplied to x minus c raised to n. Okay. Sorry. This is n plus 1 pala. Hindi pala ako. This should be n plus 1. f n plus 1. The n plus 1 derivative of the function at z over n plus 1 derivative x minus c raised to n plus 1. We can take a look at the Taylor's theorem. So ito siya. Okay. So medyo namali ako ng sulat. Okay. So n plus 1 siya. Okay. So that's the remainder. Okay. And the error is its absolute value. Okay. I'm getting the error because what was given in the problem was error. Okay. So this is the absolute value of f n plus 1 derivative of f at z over n plus 1 factorial multiplied to x minus c n plus 1. Okay. Now, let's now work on the what we know so far. Okay. Our f of x is ln of x. Okay. Its nth derivative, we were able to get its nth derivative as negative 1 raised to n times n minus 1 factorial over x raised to n. Okay. This is f n z. I mean x pala. Sorry. Okay. Ano ba ang alam natin? Tama na. This is the nth derivative. Okay. Yeah. So what we know of the value of our x is 1.2 and our polynomial should be centered around 1. Okay, those are the given. Tama. So this is our x. This is our center and the error. Okay, we would have our error to be less than 0.001. Okay, 0.001. 0.001. Okay. So these are what we know. Okay. So now the error is actually this one. Okay. So we would like this error to be less than 0.001. Okay. But let us first evaluate this error. Okay. So the error, okay, at 1.2, because that's the value of our x. Okay. is given to be this one, the n plus 1 derivative of f at z. Okay, so which means we will get the next derivative after this one. And that simply just we just have to replace n with n plus 1. Okay, so this becomes simply negative 1 raised to n plus 1. N here is n plus 1 minus 1, so that becomes n factorial over. And here, this is z. Okay, this is z. So we will have to just simply make it as your x to be z. So this is z raised to n plus 1. And then let's multiply it by 1 over n plus 1 factorial. So 1 over n plus 1 factorial. Okay. And then multiply it by our x is 1.2. So this is 1.2. And our c is 1. So raised to n plus 1. Okay. So that's how we evaluate your error. Okay. Now, since this is under the absolute value, we can simply ignore this because that just gives us the sign. Okay. So we can have this as we can ignore that one. Okay. So we'll mark this as cancelled. Okay. Here also, since we are dividing this and this, okay, we are dividing this and this here. We take note. Okay, we take note that n plus 1 factorial is n plus 1 multiplied to n factorial. Okay, so we can actually simplify this by canceling this one out, and then what is left is n plus 1. So we will replace it with n plus 1 instead. Okay, so your error now becomes, your error at 1.2 becomes 1.2 plus 1 is 0.2, okay, raised to n plus 1, okay, over z raised to n plus 1 multiplied to n plus 1. Okay, so that is your error at 1.2. Okay. Now, we take note that our z, although we know that our z is between x and z, and your c is 1, your x is 1.2. So we know that your z is between this. Okay. But the thing is that the expression 1 over z raised to n plus 1, okay, since we really don't know what, number one, we really don't know what z is. Okay, we really don't know what z is. But given that your z is within this interval, okay, you know that this number would be less than less than 1 also. Okay. If z is actually 1, okay, z is 1, and z is 1.2, that's even less than that's even less than 1. Okay. So that we will be able to establish an upper bound, okay, for our error. Let's simply use an upper bound, okay, of error of 0.2 raised to n plus 1 over n plus 1, okay, for your error. Okay, let's simply use this as your upper bound. Anyway, if you it's either this, that's the maximum, okay, and the minimum, and a lower bound for your error would actually be a number. If you substitute 1.2 here, we can evaluate z 1.2 raised to n plus 1, knowing whatever n is. Okay, if ever we know what n is. Okay, but what we're really sure of is that this would be a number that is less than 1. This would be a number that is less than 1. So therefore, if we actually multiply this number, which is less than 1, into this, it would actually lower down, or it would actually result in a lower number, and in a lower value. So instead of doing that, since we really don't know what the exact value of z is, okay, we'll just simply use this factor, so 0.2 raised to n plus 1 over n plus 1 as the upper bound of your error. So that's the maximum error that you can have. Okay. And we would like to set this maximum, this error, to be less than 0.001. Okay. So you would like to set that error to be less than 0.001. Now, what we really would like to know here is the value of n, because we would like to know the order of the Taylor polynomial we would like to write off here. Okay. So since it would be kind of tough to solve this by hand, we can actually just use trial and error for this one. Okay, so we can tabulate the value of n and when it would become and when this ratio would become less than 0.01. Okay. So here is that table. Okay. So for n, okay. Remember that we're evaluating 0.2 raised to n plus 1 over n plus 1 here. Okay. So we'll try to substitute n from 1 to 8 and determine when, okay, and then determine when the error would be less than 0.01. This entire thing would be less than 0.01. So this is more than 0.01. Um, this is still more than 0.01. This, okay, loss out pala natin siya. Okay, this is less than 0.01. So we find that n equals 3. Because at n equals 3, the error, okay, would be somewhat like 0.004. Okay, so that would imply that we need a third order polynomial um, P3, okay, for ln of x, okay, so that the error would be the error would be less than 1. Okay, you can actually try that by okay, you can actually try that by trying to write a so since we are trying to write a third order Taylor polynomial for ln of x, so your f of x is ln of x, okay, so its first derivative, okay, is 1 over x. Its second derivative is negative 1 over x squared. And its third derivative, okay, is positive 1 over, 2 over x cubed. Okay, so those are your derivatives, no? So at c equals 1, okay, your f of 1, okay, so at c equals 1, so your f of 1 is 0. This is ln of 0. I mean ln of 1, so 0. Your f prime of 1, okay, is 1. Okay. Your f double prime of 1 is negative 1. And your f triple prime of 1 is 2. Okay. So your Taylor coefficients are a0 equals 0 because this is f of 1 over 0 factorial. So f of 1 is 0. So this is 0 over 1, 0. Your a1 is f prime of 1 over 1 factorial, okay, which is 1 over 1 or 1. Your a2 is f double prime of 1 over 2 factorial, which is negative 1 over 2. Okay, and your a3 is f triple prime of 1 over 3 factorial, which is 2 over 6 or 1/3. So those are your Taylor polynomial coefficients. So we can write now P3 of x. Okay. We can now write P3 of x, your Taylor polynomial, to be 0, 1 times x minus 1, because this is the center. Okay. Minus 1 half x minus 1 square plus 1/3 multiplied to x minus 1 raised to 3. Okay. So here, since our x here, our x here is 1.2. Okay. So if you actually use this Taylor polynomial, if you actually use this Taylor polynomial to evaluate ln of 1.2, okay, in which case x equals 1.2. So we will have here P3 of 1.2 is 1.2 minus 1 minus 1 half times 1.2 minus 1 squared plus 1/3 times 1.2 1.2 minus 1 cube. This is equal to more or less so we have 1.2 1.2 minus 1 minus 1/2 times 1.2 minus 1 squared, okay, plus 1/3 multiplied by 1.2 minus 1 cube. That gives us 0.8, that's 0.1826666. Okay, so 0.1826666. It's repeated 6 eh. So 1.21826666666. Okay, so let's put it that way. Okay. The actual value is ln of x. Okay, or ln of 1.2. Okay, so ln of 1.2 evaluates to, okay, so the natural logarithm of 1.2 is 0.1823. 0.1823215568. 1823, 0.1823 21 5568. If you actually subtract this, they are actually different in this. So that's 3. 0. I'll never mind all the other digits. I'll just mind this one. So 0.0300. Okay. The actual error. Okay. Not the actual, but the this error is actually 0.03. What we're being asked is to provide an error that is less than 0.001. Just 2 zeros, right? 2 zeros. So the error that we are being asked is 0.001. So there, we were able to achieve that level of error, okay, less than 0.001 error, okay, with three terms of your approximating polynomial. Okay, so that is how we remember that when you are trying to obtain the upper bound for the error, okay, more or less that would just be simply, okay, more or less that would just be simply ignoring this this factor. So the upper bound of the error in most cases, but you have to really inspect this with your with the given expression. But in most cases, it would be x minus c raised to n plus 1 over n plus 1 factorial. That's the upper bound of your error in most cases. Okay, but not all. In most cases. Okay, but you really have to inspect them on a case-to-case basis. Okay. In example 42, we were not able to. The reason that we have to is that this error actually contains a sign of j, which prevents us from evaluating, since this is the first thing. This is the very thing that we are trying to estimate. Okay. In the case naman of in the case of example 43, we can simply ignore this factor because multiplying this, okay, with this one within the interval, okay, or within this interval, we just make it less than this value. Okay, we make it less than that value. So therefore, let's just simply use this as the upper bound for your error. And it's a safe, upper bound. Okay, most of the time it's a safe upper bound. Okay. So that's that is your Taylor polynomial. Okay. And in the next lesson, we will be able to expand the idea to more functions. Okay, by recognizing that the Taylor polynomial is actually a power series. Okay. So